A warm greetings to one and all. In this session, let's solve an example problem using principal component analysis. Now let's solve the problem using principal component analysis. Given the following data set, then we have to reduce the dimensionality from 2 to 1 using principal component analysis, that is PCA algorithm. The data set is consisting of example 1, 2, 3, and 4, and it holds the features x1 and x2. So the data set is represented in two-dimensional graph. We can see here. That is, the first point is 1, 1, and the second point is 2, 1, and the third point is 2, 2, and fourth point is 3, 2. In step 1, we need to calculate the mean values. The formula which is used to calculate the mean value is sum of all the observations divided by total number of observations. So we have to calculate the mean value for the feature x1 and x2. So we have four values. That is 1 plus 2 plus 2 plus 3 divided by 4, which is equivalent to 2. So the mean value for the feature x1 is 2. Similarly, we need to calculate for the feature x2 mean value. That is, the mean value of x2 is equivalent to 1 plus 1 plus 2 plus 2 divided by 4, which is equivalent to 1.5. So the mean value of feature x2 is 1.5. So now we can plot this mean value in the input graph. You can see here the mean value comes here, that is mean of 2, 1.5. In step 2, we have to calculate the covariance matrix. The covariance matrix S is represented as covariance of x1, x1, covariance of x1, x2, covariance of x2, x1, covariance of x2, x2. So first let's find the value for covariance of x1, x1. The formula is 1 divided by n minus 1, summation of k is equal to 1 to n x1k minus x1 bar the whole square. So now we have to expand this formula. That is 1 divided by n minus 1 into x11 minus x1 bar the whole square plus x12 minus x1 bar the whole square plus x13 minus x1 bar the whole square plus x14 minus x1 bar the whole square. So now we have to substitute the values for this formula. So we know that 1 divided by n minus 1. So n is nothing but total number of examples. We have 4 examples here. So 1 divided by 4 minus 1. So we get here. In next step, we have x11 minus x1 bar the whole square. The value for x11 should be chosen from the future x1 and example 1. The value is 1 and the mean value is 2. That is x1 bar value is 2. So 1 minus 2 the whole square. The next term is x12 minus x1 bar the whole square. So the value for x12 should be taken from the future x1 and example 2. The value is 2 and the mean value is 2. So 2 minus 2 the whole square. The next term is x13 minus x1 bar the whole square. The value for x13 should be taken from the future x1 and example 3. The value is 2. We have to subtract it with the mean value 2. So we get 2 minus 2 the whole square. Next plus x14 minus x1 bar the whole square. So the value for x14 should be chosen from the future x1 and the example x4. The value is 3. We have to subtract it by the mean value 2. So we have 3 minus 2 the whole square. So now we have substituted the values for this formula. The final value after substituting and calculating we get 0.666. The next step is calculating the covariance of x1, x2. The formula is 1 divided by n minus 1 summation of k is equivalent to 1 to n x1k minus x1 bar into x2k minus x2 bar. If we are expanding this formula, we get 1 divided by n minus 1 x11 minus x1 bar into x21 minus x2 bar plus x12 minus x1 bar x22 minus x2 bar plus x13 minus x1 bar into x23 minus x2 bar plus x14 minus x1 bar into x24 minus x2 bar. So now we have to calculate the values for x21 similar to x11 as we have done in the previous step. So what we have to consider here is we have to consider the feature x2 and the example 1. The value is 1 for x21. Similarly, x22 by using the values of x2 feature and example 2 value, that is 1. So this is the value for x22, and the value for x23 is by considering the feature x2 on example 3, that is 2. And for x24, by considering the feature x2 on example 4, the value is 2. So after substituting this in this formula, we get the value as 0.33. So next we have to calculate the covariance of x2, x1. Since it is equivalent to covariance of x1, x2, we can write the value as such here. That is 0.33, which we have calculated earlier. So next we have to find the covariance for x22. The formula is 1 divided by n minus 1, summation of k is equivalent to 1 to n, x2k minus x2 bar the whole square. So we have to expand this formula. We get the equation as such. Now we have to substitute the value, and the final value which we have received for covariance of x22 is 0.33. So now we can write the covariance matrix S value in turn as a whole. So S is equivalent to covariance of x1, x2, covariance of x1, x2, covariance of x2, x1, covariance of x2, x2. So by substituting the values as we have calculated till now, that is 0.67, 0.33, 0.33 and 0.33 is the value for our covariance matrix S. Step 3 is calculating the eigenvalues. The formula which we are using here is determinant of S. S is nothing but a covariance matrix which we have calculated in the previous step, minus lambda into I. I is nothing but the identity matrix. The value for I is, that is the identity matrix is 1, 0, 0, 1. So in next step we have to multiply this identity matrix with lambda value. So we get the value as lambda into identity matrix, that is 1, 0, 0, 1. If we multiply this, we get 1 into lambda as lambda, lambda into 0 is 0, lambda into 0 is 0, lambda into 1 is lambda. So this is what lambda into I value. Next we have to find the covariance minus lambda I value. So we know the covariance matrix value that is calculated in the previous step, that is 0.67, 0.33, 0.33 and 0.33. And lambda I matrix value is lambda 0, 0, lambda. So we have to subtract these two values. If we subtract this, we get the value as 0.67 minus lambda, then 0.33 minus 0. It can be written as 0.33. 0.33 minus 0 is 0.33. 0.33 minus lambda can be written as 0.33 minus lambda. So we know that the determinant of the matrix A, B, C, D can be written as AD minus BC. So now we can convert this matrix, that is S minus lambda I, as this form. So we'll be getting as determinant of S minus lambda I is equal to 0.67 minus lambda into 0.33 minus lambda, then minus 0.33 into 0.33. So that is what we have written here. In next step, we can simplify this. We'll be getting the value of 0.211 minus lambda plus lambda square minus 0.1081. So further simplifying, we'll be getting the value as lambda square minus lambda plus 0.1122. So using the quadratic equation, that is lambda is equal to minus b plus or minus square root of b square minus 4ac divided by 2a. We can find the values for lambda. So we get the value for lambda 1 as 0.87 and for lambda 2 as 0.13. In step 4, we have to calculate the eigenvector. It is represented as capital U and the values are U1, U2, which is the column matrix. In order to find the values of U1 and U2, we can use the formula S minus lambda I into U, and it is assigned to 0. In previous step itself, we have calculated the value for S minus lambda I. We all know that S is the covariance matrix. So the value for S minus lambda I is being calculated here. So we can substitute the same value in this step also. So after substituting this S minus lambda I and the value for U, that is U1, U2 column matrix. So now we can simplify this. That is 0.67 minus lambda into U1 plus 0.33 into U2. 0.33 into U1 plus 0.33 minus lambda into U2. So by considering these two rows as a separate equation and assign it is equal to 0. So now we get two equations. So the first row is assigned as equation 1 and second row is assigned as equation 2. In order to find the values of U1 and U2, I'm just considering this first equation and I'm writing it as 0.67 minus lambda u1 plus 0.33 into u2. So now we have to simplify it. So after simplifying it, I'm bringing this positive term to the right hand side. That is 0.67 minus lambda into u1 is equal to minus 0.33 into u2. Since we need to find the values of u1 and u2, this equation is equated to some term that is t. So we are rewriting it as u1 divided by minus 0.33 equal to u2 divided by 0.67 minus lambda, which is equal to t. So now we can write the values of u1 and u2 in terms of t. That is, u1 is equal to minus 0.33 t, u2 is equal to 0.67 minus lambda into t. So by substituting the value for t, that is t is equal to 1, we can get the values of u1 and u2. The values of u1 and u2 are 0 minus 0.33 and 0.67 minus lambda. To find principal component, we have to consider larger lambda value, that is larger eigenvalue. We know that lambda 1 is equal to 0.87 and lambda 2 is equal to 0.13. This is the largest value, so we have to use this value only wherever the lambda value is required. So u1 is equal to minus 0.33, 0.67 minus lambda. So instead of this lambda value, we can substitute the value 0.87 wherever this value is required. In step 5, we have to calculate unit eigenvector E1. So for that, we have to calculate the distance of U1. We are using the Euclidean distance formula, that is square root of x2 minus x1 the whole square plus y2 minus y1 the whole square. So here we have x2 and y2 values. We don't have x1 and y1 values. So we can consider that as origin and we can have it as 0, 0. So instead of x1 and y1, we can substitute the value 0. So it can be written as distance of u1 as square root of minus 0.33 the whole square plus 0.67 minus lambda the whole square. So after simplifying this, we get the distance value of u1 as 0.39. So now we have to calculate the unit eigenvector E1. So the formula is E1 is equal to the unit value, eigenvalue, that is minus 0.33 divided by the distance of U1. Similarly, 0.67 minus lambda divided by the distance of U1. We know the value of U1 and also the lambda, which we have chosen already. So by substituting these values, we get the unit eigenvector value as minus 0.85 and minus 0.513. So we have calculated the unit eigenvector using the largest eigenvalue lambda 1. So we can calculate the unit eigenvector E2 with the help of this smallest eigenvalue lambda 2 also. So in that we will be getting the unit eigenvector E2 value. So after substituting the value as we have done earlier, we'll be getting the value for E2 as minus 0.85 and 1.385. We are not going to use this value, but still we have calculated this value. So this is what the value we are going to use in the further calculations. In step 6, we need to calculate first principal component values. So with the help of input value, mean value, unit eigenvector value, we can substitute these values in this formula and we can obtain the first principal component value. In this formula, we can substitute the value of E1, that is unit eigenvector value, and we can find transpose. So in that case, the column matrix will be converted to row matrix. And by considering K as 1 here, we can expand this matrix as x11, x1 bar, x21, and x2 bar. So we'll be getting it as minus 0.85 minus 0.513 into the matrix that is x11 minus x1 bar, x21 minus x2 bar. So we can substitute the values of x11 with this value 1 and for x21 with the value 1. And we have the mean values for x1 bar and x2 bar as 2 and 1.5. So if we are substituting these values in this formula, we get the value as such. The final simplified value was 1.1065. We have to perform the same calculation again by considering K is equal to 2. We know the E1 transpose value which we have calculated in previous step. By substituting the value K is equal to 2, we can expand this matrix, that is x1 to x1 bar, x2 to x2 bar. So we get this equation. By substituting the values of x12 as 2 and x22 as 1, we get this values. By simplifying this, we get the final value as 0.2565. So again, we are calculating the same formula by substituting the value k is equal to 3. We know E1 transpose, which we have done in the previous step. By substituting the value k is equal to 3, we get x1 3, x1 bar, x2 3, x2 bar. So this is the formula we get. By substituting the value of x1 3 as 2 and x2 3 as 2, we get this values. By simplifying this, we get the final value as minus 0.2565. We are performing the same calculation again by considering k is equal to 4. We know E1 transpose value. By substituting k is equal to 4 in this matrix, we get the expanded matrix as x1 4, x1 bar, x2 4, x2 bar. So like this will be obtained, and we have to substitute the value for x1 4 as 3 and x2 4 as 2, and we have to substitute the mean value for x1 bar and x2 bar. We get the values as such. So if we simplify this, we get the final value as minus 1.1065. We have 4 examples for both the features x1 and x2. So we have found the first principal component for example 1 as 1.1065 and for example 2 as 0.2565, for example 3 as minus 0.2565, for example 4 the value is minus 1.1065. So this is the final value for our first principal component using the unit eigenvector E1. The principal component values which we have calculated is being updated along with the input data values. Next, by considering the mean value as origin, that is 0.0. Here we are considering this mean as 0.0 and the eigenvalue E1, the value is minus 0.85 and minus 0.513. So this is x value and this is y value. Since both x and y are negative, we have to consider this quadrant where x is negative here and y is negative here. The x value may comes around here, that is minus 0.85, and y value may comes around here, that is minus 0.513. Based on this point, we can draw an eigenvector and cause the eigenvector through the origin. So this is what the eigenvector for the eigenvalue E1. So similarly, by considering the eigenvalue for E2, and we are considering same origin, that is mean value as 0, 0, origin 0, 0, and considering the eigenvalue E2, that is minus 0.85 and 1.385. Here x value is negative and y value is positive. So by considering the point minus 0.85 as here and the y value as 1.385, so the value may plot around here. Through this point, we can pass the eigenvector through the origin. So we'll be getting the eigenvector in this direction for eigenvalue E2. We are not going to consider this E2 value for our next upcoming updation value. So we are considering the eigenvector E1 and we are projecting the data points to the eigenvector E1 as if we have shown here in this diagram. So we are projecting the data points to the eigenvector E1. The final plot, that is from two-dimensional data point which has been reduced to the one-dimensional data points, is being given here in this diagram. This is the output. After executing the code, I have obtained it for the same code, input data values. So these are all the input data values, that is the original data values, and these are the projected values. So we can see here the projected value 1.065 is being present here and 0.2565 is being present here and minus 0.2565 is being presented here, minus 1.065 is being plotted here. So we have converted the two-dimensional data points to one-dimensional data points using principal component analysis. So here we have considered only one principal component. So if we require, we can have 3, 4, 5 up to n number of principal component as of our requirements for the applications. So hope you are clear in principal component analysis with this example problem. Thank you all.